Welcome to the course on fundamentals of MIMO wireless communications. We have been looking closely at the small scale propagation models. Right now we have covered the flat fading and frequency selective fading. So we have covered the time and frequency dimensions. As you have noticed that we have specified the channel, the wireless channel, in the time dimension, in the frequency dimension, in the space dimension. Last time we have said that in the time dimension we have classified it as slow fading and fast fading. We have described the details. In frequency we have also described there is flat fading and there is frequency selective fading. So now we reach the spatial dimension, which we are going to describe, which could be poor scattering or rich scattering. So we will see how this thing happens. So to begin with, we will base our expression on whatever we have studied over here. So based on that, this will be helpful to describe. So that's why these will become foundations. So that's why we have spent quite a lot of time on those topics. So if we consider that the mobile is moving, and let's say there is some measurement at this point. Let's consider that there is a receive antenna, and that the mobile is moving in this direction, and over a certain time, that is delta t. If we consider a certain time delta t, in this duration of time the mobile would cross a distance, let's say delta x, which is very small in this unit of time. So delta x is equal to v, that is the speed of the vehicle, times delta t. So in this distance the receive antenna may have been at a location which is separated by delta x, or the vehicle could have moved over there. So since we know that v by c times fc equals to fm, right, therefore we could also write v is equal to fm by fc times c, and we could write delta x as fm by fc times t times delta t, taking that delta x equals to v times delta t. Therefore delta x is v times delta t, or we could also have fm delta t, that means this times delta t is equal to delta x times fc divided by c, and since c is equal to fc times lambda or lambda c, so you could write lambda c equals to c by fc, or which is delta x upon lambda. So this particular variable or the product which we have written over here is something which you have encountered before. So you already know that for isotropy scattering, we have phi hi delta t is equal to omega p by 2, where omega is the total received power, j0 is the Bessel function of the first kind of zeroth order, 2 pi fm delta t. This expression we had derived before for the correlation. So basically when we studied this flat fading condition, and we were looking at the Doppler spectrum, that is how it would go ahead. So we studied the correlation function, based on which we looked at the Fourier transform of that, and we arrived at the Doppler spectrum. So this is the correlation function. So now we could, instead of making it a function of delta t, we could write phi hi using the same expression, a function of delta x, instead of making it a function of delta t, by using this translation, and which would become omega p by 2 j0 2 pi fm delta t is delta x upon lambda. So this basically tells us that if we are spaced apart by delta x, then the correlation of the signal at this point and this point could be expressed by this function provided we have isotropic scattering. That means provided there is isotropic scattering. Remember, this was derived when p theta was taken to be equal to 1 by 2 pi. That means there is equal probability of rays arriving from all directions. So there would be equal probability of rays arriving from all directions. Under such condition, we could use the already derived expression to arrive at the correlation of the received signal, which is separated by a certain distance delta x as a function of lambda. This is very important, and if you would look at the correlation of alpha delta x, alpha is the mod of h of t. So that would be pi by 16. This is just a normalizing factor, omega p j0 squared 2 pi by lambda delta x. So this is also derived directly from the expression of correlation of alpha, and similarly it will be for alpha squared. So if you would look at this particular expression, what you can get is that at delta x equals to nearly 0.38 lambda, mu of alpha delta x is equal to 0. So from this is what you get. So that means under such a condition, that means under the condition where there is isotropic scattering, that means rays arriving from all directions with equal probability, if we have the spacing separated nearly around lambda by 2, this is roughly lambda by 2, then you get uncorrelated signals. So if I space them at lambda by 2, this is very important result that we have. So this we can remember that when we have two antennas and we are looking at these two antennas. So when these two antennas are separated by lambda by 2, the signal in this antenna and the signal in this antenna would be uncorrelated. Now as we bring them closer and closer, the signals are more and more correlated with each other. So this is one fundamental result, and we have derived this for the case where there is equal probability of arrival from all directions. So with this we basically move. So now if we try to categorize it in terms of rich and poor scattering, we could get situations where we can have the case that is rays arriving from all directions with equal probability, and there could be rays arriving at particular direction. Here p theta equals to 1 by 2 pi, here p theta is not 1 by 2 pi, and we have seen certain cases. In one case we have seen there is a specular component, that is there is a k factor. The other cases we have seen the Doppler spectrum to be Gaussian and not a Jake spectrum. So there are certain such situations which we have already seen for Doppler conditions. So what we will now look at is to describe this particular situation is described by means of angle spread. See here, when we looked at the dimension of time, we had said there is when it is slow or fast fading, we had described in terms of the Doppler spread, here we had the term delay spread, and similarly here we would have angle spread. In this case we had transmitted a single tone, but that was received as a Jake spectrum when there was 2D isotropic scattering or some other ways. Here when a delta function was transmitted, what was received was echoes of the delta function in the delay axis. So a delta function was spread in time, and we had in the delay axis we had the delay spread, the excess delay, and here even though there is transmission from one direction, because of scattering from multiple directions, you get an angular spread of the received signal. You get an angular spread. So these are the description in the 3 dimensions, and here we will see what are the effect of it and how it is described. So typically if you look at a mobile station, usually the base station is at a height. In most cases the base station is at a height, and the mobile is usually surrounded by buildings and lot of scatterers. That is usually the scenario. That means the rays that come, they get reflected from different scatterers and so on. So, usually at the mobile location we are going to get signals arriving from all directions with equal probability. This is more or less true, but if you look at the base station, I mean suppose there are multiple antennas at the base station, it is not true that rays are coming from all directions with equal probability. So, that means the angular spread at the mobile is not the same as the angular spread at the base station, and this is very fundamental. This is also very important in deriving certain results. So, we describe angular spread as the spread of angle of arrival. As a spread of angle of arrival, or AOA of the multipath components. Multipath components, or the angle of departure. If it is the receiver, it is angle of arrival. If it is transmitter, it is angle of departure. So, if psi A of theta is the average power as a function of angle of arrival, then we could define theta root mean squared as square root of integrate from minus pi to pi theta minus theta bar, the mean angle of arrival psi A, that means the power at the receiver coming at different angles, the theta divided by the normalization factor, which is psi A of theta d theta, and theta bar is the mean angle of arrival, which could be again defined as minus pi to pi theta psi d theta, again divided by the normalizing factor psi A of theta d theta. So, this is basically the average power as a function of angle of arrival. So, as a function of theta, we are normalizing it by at the denominator, and this particular thing would cause space selective fading, and usually you would define coherence distance, you would define the term coherence distance. See, again if we go here, we had coherence time in the time analysis, we had coherence bandwidth in the frequency analysis, and here we have coherence distance in this space analysis. So, in coherence time we said that coherence time is inversely proportional to the Doppler's frequency, the max Doppler frequency. Coherence bandwidth is inversely proportional to RMS delay spread, or coherence time is inversely proportional to the Doppler spread. Coherence bandwidth is inversely proportional to the delay spread. Similarly, coherence distance would be inversely proportional to the angle spread. This means that as the Doppler frequency increases, the coherence time decreases. That means the faster it fluctuates, the distance of time for which it is coherent is less. Similarly, over here, the more is the spread, less is the coherence bandwidth. Here also it is talking about the same thing. More is the distribution of the angle of arrival, lesser is the coherence distance, and less is the spread, larger is the coherence distance. So, that means what we can say from this, coherence distance is inversely proportional to angle spread. Let us write this. So, that means we can say that at the receiver, that means in this point where signals are arriving from all directions, the coherence distance is smaller because angular spread is larger, and here coherence distance is larger, much larger, because angular spread is less. So, at the mobile, it's advantageous for us that we can place two antennas which are close to each other. So we can place two antennas which are close to each other and they are uncorrelated. So when they are close to each other, they would be uncorrelated, and whereas at the base station they need to be spaced far apart to get uncorrelated signal. Now just look at the description that we gave at this point is probably we required a larger coherence time. We would like to have probably larger coherence time. Of course, there are merits and demerits. Again, we may like to have a larger coherence bandwidth, again with merits and demerits. With coherence distance, same does apply. That means here in one case when we are discussing equalization, we said that if the signal is experiencing slow fading, that means over the signal bandwidth there is no over the symbol duration there is no fluctuation, and over the signal bandwidth there is no fluctuation. That means if we would draw a signal time frequency grid in a way that let this be the frequency axis, let this be the time axis. So if this is the time frequency space a signal occupies and the channel is nearly flat over this space, equalization would be easy. Whereas when we talk about the spatial dimension, we have the x axis, let's say. So we are kind of finding out over what distance would the signals be uncorrelated, is defined as the coherence distance. So now in this case what is of interest to us is how close is it. The closer it is, the better it is for us compared to the coherence time or coherence bandwidth situation. Here we would have loved to have a longer coherence time because and a longer coherence bandwidth because we could do with easy equalization. Of course, there are problems because that would mean once the signal is in a certain state because of the channel, the signal or the channel won't come out of that state very fast if the coherence time is long or if the coherence bandwidth is very large. Whereas here the situation is not a function of time or frequency, it's with space. So if coherence distance is small, we could place two antennas close together. So if we have a mobile which is, let's say, 6 inches or 5.5 inches wide, and if we take the frequencies of operation, let's say 2400 megahertz or so, we could easily place two antennas on that phone. Whereas at the base station we need to place them far apart, but again the distance would be manageable. Now this is one of the very interesting things that we have at hand. Now if we look at this particular expression, what we see is that it is also a function of lambda. That means longer lambdas would mean smaller values over here, so that would affect the coherence distance. So there again what we get is smaller very small values of lambda would mean again the coherence distance is short compared to larger values of lambda. So the frequency is also affecting the operation over in this particular dimension as well. So usually we would find that at the base station the coherence distance at the base station, that means this particular picture, at the base station the coherence distance is roughly, let's say, 5 lambda, whereas here it would be nearly 0.5 lambda roughly. I mean that's how it is. So if you would take 2D isotropic scattering at lambda by 2, it's uncorrelated. At 0.25 this correlation becomes 70% or so. So we would like to have it lambda spacing antenna spacing lambda by 2 in order to be uncorrelated. Whereas at base station this distance becomes around 5 lambda or so, because angle of arrival is nearly around 20 degrees to 30 degrees in that range. Okay, so this is one of the very important things that we are moving into when we look at the spatial channels. So now we would like to look at one particular characteristics of the channel, and that is known as wide sense stationarity uncorrelated scattering, because that we would require to describe what is called a homogeneous channel, and this is one of the important assumptions that is made in the study of wireless channels. So if we look at the expression for the channel coefficient, that means we would usually write it as h t comma tau, and we take h conjugate at t plus delta t comma tau, and we take the expectation of it. What we are talking about is the correlation in time. So, this is t, right, and we said that this is r tau r delta t comma tau. That means this is not dependent on t, it is dependent only on the lagged time between the two channel coefficients. And if you take the Fourier transform, and we would write the scatter function as s is equal to minus tu by 2 to tu by 2 h of t comma tau e to the power of minus j 2 pi, and let us put this frequency nu t dt. That means I have taken the Fourier transform in the time domain, and in the limit that tu tends to infinity, we are going to get and we take expectation of s tau comma nu. I am just changing the location of the variable so that it is easier. S conjugate tau comma, we have nu 1 and nu 2 at two different frequencies. This would be equal to 0 if nu 1 is not equal to nu 2. This is one of the results that we are using. This comes from Whitesense stationarity. If you would remember, we applied Whitesense stationarity to arrive at this particular condition. Now, again, if you would use Whitesense stationarity on this and you look at the Fourier transform of this, that means you are looking at the scatter function, take the expectation of it, you are going to get this result when nu 1 is not equal to nu 2. What does it mean is that two different Doppler frequencies, they are uncorrelated. I mean, that means the channel at two different Doppler frequencies are uncorrelated, and this is because of a famous paper by Bellow 1963. Those who are interested, they can look at it. And along with that, there is also this uncorrelated scattering, US uncorrelated scattering, which says that expectation of h of t comma tau 1 times h of t comma tau 2 is equal to 0 if tau 1 is not equal to tau 2. Now, what it means is that if we look at this diagram which we had drawn before, if this is the tau axis and this is the t axis and this is h of t comma tau. So, at tau 1 we have an impulse, that means we have sent an impulse, we have received an echo, and this is fluctuating with time. Then at another tau 2, this also we have seen, there is another echo which is coming. So, what it says, at every instant of time, if we try to take the product and do the averaging, the result is 0. That means this and this are not correlated, these two are uncorrelated. So, that is the result of uncorrelated scattering. Now, this would give rise to the lagged frequency correlation or expectation of h f1 tau h1 t times h conjugate of f2 t. This is equal to the correlation function of delta f at t. This we have already seen. What it means is that if we take the Fourier transform, that means now we are taking the Fourier transform across this tau e to the power of minus j 2 pi f tau d tau integral 0 to tau max of h t comma tau. So, this is what we have to take. So, we are taking at two different frequencies. So, if we are getting it as a function of frequency, we get the transfer function, the channel transfer function. So, if we make the assumptions that at two different delays the channels are uncorrelated, the result we get is the frequency correlation function is not dependent on the frequency, but only on the lag. That means, if I take the Fourier transform across this axis, I am going to get the transfer function, that means h of f at a particular instant of time, this is f. So, the correlation between this point in frequency and this point in frequency is dependent only on the gap and not an f1 and f2. So, again, if I would take these 2 points in frequency f3 and f4, if this gap and this gap is the same, the correlation would be the same. So, that is the lag frequency. So, this is the famous Whitesense stationarity uncorrelated scattering channel model. So, with this we would move on to describe the homogeneous channel for spatial condition. So, basically here what we have talked about is second order stationarity in the time and frequency domain. So, that is what is described by wide sense stationarity uncorrelated scattering. So, similarly, there is also the second order stationarity in the space domain, and that gives rise to the homogeneous channel, the homogeneous channels. So, here the assumption that we make is that the statistical behavior of h tau t d. Now, we have the third dimension. This is the delay, this is the time, this is the space, okay, is locally stationary in space over several tens of the coherence distance dc. So, previously we have said that the coherence distance is inversely proportional to the angular spread, and now what we are talking about is the homogeneous channel, which says that over a certain region which is several tens of coherence distance. Distance is of course x axis or the y axis. So, that means we are talking about the y axis or x axis. So, it is the space. So, several tens of coherence distance in this what we have is homogeneous channel, that is which is described in the form that E of h tau t d and h of tau t d plus delta d is equal to the correlation function, which is a function of tau t and delta d and not of d. That means a lag space correlation, lagged space correlation. That means over a certain region in space, the correlation between two locations, the signal at this location and the signal at this location, which is separated by a certain distance, is not dependent upon this location or this location, but only upon the separation. So, that is what is homogeneous channel, and this is very important. So, along with wide sense stationarity, if we have wide sense stationarity, which gives us that the correlation function is dependent only on the lag time, and which gives rise to that the channels at two Doppler frequencies are uncorrelated. Along with, we have uncorrelated scattering, which gives us that the channel coefficients at two delays are uncorrelated, and that would give us that the channel at two different frequencies are correlated only by the separation in frequencies, and that is extended to homogeneous channels. That means the signals at two different points in space are correlated as a function of only the separation distance and nothing else. So, here it is giving rise to separation as delta t, here it is separation in delta f, and here it is separation of delta d. So, this again gives rise to the result that signals coming, again s is the scatter function at two different theta 1, and if I take the scatter function at tau 2 theta 2, this would be 0 if theta 1 is not equal to theta 2. So, that means signals coming at two different directions are uncorrelated. That is what this gives results in. So, that means two different theta 1 signals at these two are uncorrelated, signals at tau 1 and tau 2 are uncorrelated, signals at f1 two different Doppler frequencies are uncorrelated. So, that is what the dual description of wide sense stationarity, uncorrelated scattering, homogeneous channels give rise to. So, this particular channel S is described as h of tau t x, instead of d we are writing x, is equal to minus pi to pi s of tau t theta e to the power of minus j 2 pi sin theta times x by lambda c d theta. So, this is what we have the expression, the relation between H and S. So, the Fourier transform relationship between H and S. So, this is also known as a scatter function. So, this is the arena in which we will be discussing the rest of the course. So, this is very, very important assumption that we will use in whatever analysis that we are going to do in this work. Thank you.